Welcome back! So far in the series, we've looked at how various data structures are used to build common abstract data types, which provide the building blocks to work with data in our programs. Some data structures use arrays, others use linked nodes. In this video, we'll finish up our discussion of data structures by learning about hash-based data structures. Let's dive into using hash table as an example. Hash table is a very common data structure used to implement the map abstract data type that we talked about in an earlier video. To review, maps store values that can be accessed by keys. Consider this map. We want to be able to use the cats key to efficiently get back the value 80 as the page number. This is similar to using indexes to get values in an array, except the keys in a map can be any type, not just numbers, and they aren't necessarily sequential. For our hash table data structure, we actually will use an array to store the values, but we will add a function to convert from the keys to the index numbers in the array. We'll use a special kind of function called a hash function. A hash function is broadly defined as a function that takes in a value from a wide range and converts it to a value in a narrower range. You can write many different functions that meet this definition. In our case, we'll use a function that takes in any string as a parameter and returns an integer number within the bounds of our array. A very simple hash function for strings would be to take the length. Using this calculation, birds calculates to 5, cats calculates to 4, and insects goes to 7. If we combine this hash function with an array, we get a hash table data structure that works like this. Birds calculates to 5, so we put the page value for birds, which is 14, into the array at index 5. Cats calculates to 4, so that value, 80, goes into the array at index 4. Insects goes to 7. And dogs is 4. But wait, cats is already using the number 4 slot. When this happens in a hash table, it's called a collision. Collisions will always be a possibility. The nature of the hash function is that there are a larger amount of possibilities coming in than coming out. So there will always be some values, like dogs and cats, that share the same hash result. Hash tables handle this by using a list of values in each slot, for example, a linked list. Once the hash has narrowed down the search to a particular slot, the hash table then loops through the short list to find the matching value. Alright, now that we've constructed our hash table, let's see how it works. When it comes time to look up a page number, we query the hash table for our keyword, birds. The hash is calculated as 5, and the value is found at the number 5 index in the array. We get back page number 14. Let's try again with dogs. The hash is 4, so we go to the number 4 spot. Here we have multiple values, so we'll loop through until we find the one labeled dogs. 35 is our answer. In our example, we used length for our hash function, and you may notice that most of the entries ended up in about the same spot in the array. In practice, length is not the best hash function. Most English words are going to end up between 7 and 10 letters, so there would be a lot of keys that end up in the same spot in the array. In other words, there would be a lot of collisions. Your best bet is to use the hash functions already developed for your language, because they will take this into account. The only hard and fast rule for a hash function is that given the same input, it must always produce the same output. That way, when you insert birds into the hash table at index 5, every time you go to access birds again, the hash function will always calculate to 5, and it will always look at index 5. And every time you look up insects, it will always look at index 7. Let's recap what we learned about hashing data structures with a quick practice quiz. Which of the following statements is true about hash functions? True or false? Hash functions convert values from a large range of possibilities down to a smaller range. True. There are many kinds of hash functions, but they all fit this broad definition. This works great for our hash table because there are almost infinite possible keys, but our array has only a limited number of slots. True or false? All hash functions convert strings to integers. False. It is true that some hash functions do convert strings to integers. That's what we use in our example. but there are different hash functions for many different types of data, both as input and as output. True or false? Every time you call the same hash function with the same input, you will always get the same result. True. This is a crucial characteristic of a hash function. In our example, the bird key will always end up in slot number 5, every time. True or false? With hash functions, you can never get the same output for two different inputs. In other words, if you have two different keys, they will always map to two different slots in the array. False. Most hash functions will produce the same result for several possible inputs. Because of this, it's necessary to handle collisions in hash-based data structures. If you'd like to start using hash tables, the hash table data structure is built into Java as the HashMap class, and in C# as the dictionary class. Hashing is not only useful for hash tables. For example, it provides a very efficient implementation of the set abstract data type. In C# and Java, this is built in as the HashSet class. JavaScript has a map class as well, although regular objects also provide similar functionality, and it has a set class. However, each of these may or may not use hashing behind the scenes. Okay, we made it! That's our introduction to data structures. I hope you've been able to get some context for how data can be arranged in different variables, arrays, and objects to accommodate different uses. Your language has many of these concepts built in, and others available via free downloadable libraries. So, start experimenting with the shiny new tools in your tool belt.